designed with this kind of non-heme environment not to be tyrosine. Why? Hard and soft acid principle of your school level. These are all connected. So iron 3 should have tyrosine, histidine, aspartate because negatively charged, and here metal 2 says zinc, then you have bunch of histidine, neutral kind of thing. What happens? This iron 3 will pull electron density, so water will become weak, and then the other phosphate monoester gets coordinated with the other side, and then this weight attacks and breaks the bond. And this was done by Lipscomb, you have already mentioned, and Bernd Krebs from Germany. They came up with this review article, and on the 1996, a large number of these things are there. Again, the bottom line is a metal should have a water to generate nucleophile. Other splice substrate should get bound and then nucleophilic attack, but try to get more than that. And this is again to say, I can just leave this because this is what I have said already. This could be, if you have a hydroxide bridge, that bridged hydroxide can also attack because this one is coordinated, so that can attack this carbon. Both are possible. Now, lessons learned from natural hydrolysis. What you have learned? A synthetic hydrolase should satisfy the following criteria. Otherwise, your bioinorganic modeling will never work. Fine-tune the pK of coordinated water to render it more acidic compared to free water to provide a metal hydroxide as nucleophile at pH 7. You cannot have a water which is will deprotonate in 11 pH, then something is wrong. Because your body is close to 7 pH. So it's like that. For a mononuclear system, 2 cis-labile sites should be available. One to bind, another to attack. One to bind the substrate, the other to inertia. For a dinuclear system, at one metal center the substrate binds, and the nucleophile generated on the other center brings about the nucleophilic attack. Activate the substrate towards nucleophilic attack and stabilize the transition state and release the product in a reasonable way. If these conditions can be satisfied by any compound you make in your laboratory, you can claim that I have done a reasonably good synthesis of a hydrolytic enzyme mimicry. So what we did, and then catalytic efficiency of metal hydrolysis, choice of metal ion is important. Which metal ion do the job? We know nature does zinc, but very few people attack that problem. Why zinc? We know the zinc. Did you compare with all other metal ions with the same geometry? Those kinds of questions we wanted to ask. So then if you need what metal ion is the best? Let us see. Availability of labile or vacant quadrant sites and suitable disposition of the labile site so that nucleophile can approach the substrate. So I have one water here, another water this side. So this OH ion can never attack this thing in a whole life. Or here substrate binds and the water is on the other side. Nothing will happen. Or the distance is D here. Nothing will happen. So there should be nearby distance, attack takes place, and the stereospecificity, everything is very, very important. Now, availability of basic functionalities, so these things are already there in my work way I present. So given that background, some time back, we came up with these two ligands. Very simple ligand, you can prepare in your laboratory without much trouble. So you can make this compound. What is that? This OH is basically deprotonated, and that should bring two metal ions, one here in this pocket, one in that pocket. And this will be having these two, pyridyl and amine, and this should have pyridyl pyrazole and then bridging. So that kind of situation, you imagine. So bridging are common, this tag and that tag common, one CH2, one CH2, one CH2, one CH2, almost same. Only thing is terminal is different and that terminal is different. Very rigid, flexible. Why flexible? Two CH2s. Ethylene diamine, you can just manipulate. Availability of open solvent or what sites you require, otherwise you cannot do. Determine pKa values of metal to coordinated water, and you try to do hydrolysis or trans-esterification of this substrate called HPNP. It is used as the RNA model, RNA small molecule model. And we do reaction, saturation, all kinds of, and this is this HPNP. And you know it has a nice weight attached to it. So it is basically attacks and generates this kind of thing. That's why the name is trans-esterification. So special kind of hydrolysis. So this thing happens. So you have to prove that you compound have that. How could you prove? You can prove by two ways. You can prove the formation of this or formation of that. Which one is easy? Because this one will give rise to phenolate ion. So it will be 400 nanometer nice formation. More and more, that means formation of paronite or phenolate you monitor, so you know how much hydrolysis is going on. And how can you prove the formation of this? You do 31p NMR. So if you do an NMR spectroscopy, then you can also prove that those things are being generated. So we took the first compound, this ligand, and very nice, and you see two water like that. So that was our beginning of our journey. So beginning of our journey like this, nicely bridged, terminal things are there, but all compound 336, only good part is to water molecule, but coordinatedly saturated. If the waters are not impressed, it's very sleepy. So coordinatedly saturated. Now the question is, how could you break some of them so that substrate can come and get bound? If they don't do it, your compound, you can throw it in the dustbin, publish in some journal, nothing will happen. So this is the compound synthesized, and these are parameters. So important is nickel-water bond distance is like this, and nickel-nickel distance is like this. And if you remember, I showed ureas, the distance was nearby that kind of. So this is the compound composition, but this compound is this composition is structure. So we were happy. At least we have two water molecules, cis one. Distances are comparable, and bad part is all are saturated, which we don't like. But I will tell you how to manage. Then we took the other ligand. We made this kind of compound with our synthetic skill, and we could see again bridget, again everything is fine. Water and one methanol. At least, if not two water, you have one water, one methanol coordinated. That is great. And you have some acetate bridge. So again, these kinds of things should go. Otherwise, there is a problem. And nickel-nickel distance is again comparable, nice, but distance is 2.122. What tells you? That this molecule, nickel and water distance is 122, and for the other one is 2.08. Which one is more strongly bound? This one. So which one will be more acidic? This one should be. That means strongly bound means proton will be released quickly, or it will be easy to deprotonate. Keep that in mind. How do? You do potentiometric titration. To figure it out, you have two water molecules. At what pH one water becomes weight, and at what pH another water will also become weight. So you have weight kind of. And what are the things? So you can see one inflection here, two of them. And you have the curve fitting you do. And we determine the first compound. First compound, you remember that aliphatic amine and pyridine. That's one only remember, forget about other things. And you remember directly bound pyridyl pyrazole. But I wrote here 2, but I wrote here 3. Because this compound, crystallized stuff, does not dissolve in water. So to do that, we make the same compound without the pH 4 salt with the perchlorate, which we name as 3, not the 2. Structurally characterized compound is 2, and same compound with all groups we have, it is basically perchlorate salt, which is soluble in water. That is the basic difference. Now you can have here, so you see the pK values. How many waters you have each molecule? 2. And now under what condition you are doing? Because one molecule is having water, one molecule is having methanol. So one molecule has 2 water, another water methanol. But condition should be such the same. What will be 33% methanol water. So that means more and more of water and less amount of methanol to solubilize the compound. So this condition if you do, so if you have water methanol, so everything will be water now. Methanol won't be there. How do you know? You do mass spec, you can check. So we did all kinds of things and we titrated the solutions from 1 and 3, and we got similar kind of plot. And these are the pKa values. The first compound, the pyridyl and amine, 7.8 type 8.5, and the other one 7.95 and 8. So you know this value is 7.8 and this point is 7.95. So you know, pay attention to the bond length and determine pKa properly. You can really correlate now absolute scale which one will be more nucleophilic, which one will be a better attacking for the hydrolytic enzymes. So we kept that in mind. Another point, the compound 1 was like this, 2 was like this. But the condition we put it, and we could see these kind of acetates are gone, yes. So acetates are dissociated from these molecules, and you actually have this kind of species. The rigid, solvent, solvent, water, water, and then water, water becomes water weight becomes weight. These are the three species. This one to that one is pKa1, and this species to that species is pKa2. So you have two pKa's you have determined, and you have determined, hey, please don't disturb in the class. If you don't like, leave the lab. Second one, I'm telling you, yeah. If you don't like, there is too rubbish, leave the room, okay? Don't create any confusion. So then you have this, so that means two of them, hey, don't talk to him, I'm talking to you, so please, I'm giving a talk, so don't smile and talk just like that. You don't like, you don't leave, that's the concentration goes. So you have water, weight and weight. That is the way the whole thing is. So now we have one pK, another pK, but we are convinced now from mass spectroscopy that acetates are dissociated, and we proved that this kind of methanol or water coordinated in these three species. That is full proof we have in our system. And then the question is, when you have lower pH, your species is A, after that species is B, more you have alkaline species is C. What are those ABC? A is this, B is this, and C is OH. So when you have more and more alkaline medium, you will be having more and weight. Lesser alkaline, one water, one weight. Less alkaline, one neutral, water. So everything goes hand in hand. So we did that with this molecule, other molecule, everything. And this is our condition. We have to check that this one is, this kind of things are being formed. What do you do? We did the 31P NMR, and you can see just mixed cyclic phosphate, which is your this product, and that generated. So these we are monitoring. This and that. It will go and that will be formed. That is our target. And once you do it, you know HPNP gone, and you have generated the phosphate after 18 hours of the transformation of the transesterification reaction. So we followed that, and this was the condition. Condition was such that, under the same condition where you have the pKa1, pKa2 you have done, so you know exactly the species present in solution doing the job. Otherwise, there will be a vague kind of thing that maybe kind of thing would come. Then you have the conditions of various kinds of things I don't want to get into. So pseudo first order rate constants we did, and how do? You know the formation of paranitrophenol and paranitrophenolate, and you know these kind of equations. You know this equation pH equal to this. These are all our +2 level understanding of the undergraduate. So by doing that, condition you do, buffer you use, pH range you analyze, and you do the reaction. Here you know the substrate is this and complex is this 2.5. So complex is more complex than the substrate. That's the condition we followed for this kinetics. So more of complex and less of the substrate. So we did the profile, and you know this. Phosphatase like activity experiments were carried out by monitoring spectrophotometrically the absorption increase of the liberated paranitrophenolate. NEN, which is 400 nanometer, the excess coefficient is like this. So you monitor this value at that wavelength, and you follow what is slowly going on. And if K-ops you get, and find the K-ops, plot against pH, change the pH again to the experiment, change another pH again to the experiment. So as the pH profile change, you follow the rate constant of hydrolysis of or even transesterification of HPNP and monitor the whole thing. Once you get all these things, the data points, scattering, everything is done appropriately. Then you computer simulation, you do with appropriate equation, and you can determine the pKa from kinetics. And that pKa was determined from potentiometric titration. So this kinetic pKa value has been determined to be 1. That means pyridyl and amine, you have 8.64. And this value coincides with the second pKa, 8.5. So you know your active species must be this guy, where you have weight, right? But that you can determine which is the actually compound. And for the other compound is again 8.75 coincides with these pK value in bracket is the potentiometric titration, and these pK values are determined from the simulation of the data which you have got. That is the way you double check your determined pKa value and the experimental determined and the estimated pKa value, they go hand in hand. Then what you do as a function of complex to show is a first order reaction. So you can see a nice straight line. So all those things determined 33%, all kinds of things are there. And for the other compound again. Now by doing everything, so what you have now? You have second order rate constant. First order is just, and then complex determinant your dependency. So second order rate constant, first compound has this kind of value and the second compound has that kind of value. So at least you get, under these conditions, first compound is hydrolyzing better than the third compound. That is for the values is obvious. But your condition was complex more and substrate was less. That is the condition, because you can have pseudo first order condition. You can use either the substrate mode or the catalyst mode. We took one of them. Then we determine all these values, whatever you can see, this is the value. So we have uncatalyzed reaction 730 divided by uncatalyzed. Uncatalyzed reaction is very small. So first compound 730, second compound 130. So you know the first compound pyridyl and amine is better than pyridyl pyrazole directly bound because of the bond length also one and the flexibility is less in the second compound, more rigid. So you can quantify why the second compound is not that good and the first compound is a better hydrolytic enzyme. That's fine. Then you say, now I will do the other way. We will do excess substrate, the typical Michael-Menten plot of the biology. Okay? So you have more and more substrate. So once you do more and more substrate, then you see a saturation behavior. So you give substrate, yes, hydrolyzed. You give more substrate, yes, hydrolyzed. So substrates, you know, the enzyme catalysis. So that was followed appropriately. So it's a maximum velocity versus this plot. Now with this ligand the plot, other ligand is similar plot. By doing this, you have the double reciprocal plot, you know, enzyme catalysis or Lineberger plot. So you have this thing and you see the values. We got a value of Kcat by Km, that is called catalytic efficiency, 0.42 for 1 and 0.089 for 3. So this is the definition of the enzyme catalysis, and this is the second one is this, but you see value 0.42 is 0.3, 0.089 is 0.058, one is the standard pseudo first order conditions, and other one is enzyme catalysis condition. They are go hand in hand. That means either way you attack the problem, substrate you give more, or the catalyst you give more, you have the same kind of behavior. So then you have the complex, you have the Vmax, maximum efficiency to do it. You know Km, binding constant, and more strongly bound is not good as such. Kcat, association, and the energy necessary, E is what define everything is, if this is the important factor. That is, you know, 5.75, so roughly 6 for the second compound, and the first one is 65. So 6 and 65, you know, more than 10 times the first compound is a better catalyst. You can pinpoint exactly what is going on. So we have done so far some kinetics, some synthesis, some potentiometric titration, some rate constant, some pKa determination. Let us do little bit of other things also. We know in our condition, acetates are getting decomposed, liberated. Now we do an inhibition experiment. In favor of acetate, more you put acetate, the rate decreases. Inhibition experiment. So if the acetates are bound, you will never get hydrolysis. The acetates are out because then only substrate can get bound, and the attack can take place. So we do the inhibition experiments as well under the similar condition, identical conditions, and you prove the increase and the rate increases. Inhibition increases for both the compounds. So this is so far so good, and we have checked how much is getting inhibited. You do a little bit of physical chemistry. So then you know, you do Arrhenius plot. Why Arrhenius? Because you have two things are coming up, the rate as a function of temperature. So if you do rate as a function of temperature, you see this, and you do also Eileen plot. So to do, why do you do Eileen plot? To get some information about this delta H dagger and this delta S dagger. Then only you have an idea whether the compound is there. I give a substrate. Is it associative mechanism or dissociative mechanism, right? If it is associative, then delta S will be negative. If it is dissociative, delta S will be positive, because the increase of the the entropy will increase. So keeping those things in mind, we did all the experiments, and you see this is EA, energy of activation. So you determine that they are comparable. Frequency factor you calculate. Delta is dagger is positive, that is bond breaking takes place in the your transition state. Delta S is negative, meaning associative mechanism, and delta G is the value. So then everything goes hand in hand, but everything you have to learn: the synthesis of the organic ligand, inorganic compound, extra structure, titration, rate, mechanism, and all things together, a little bit of physical chemistry, all the parameters are going towards that. So far so good. And we came up with this paper a long time back, that this is the situation, bridged compound. This substrate gets bound in a binucleic mode, bidentate mode, and this nickel weight attacks this one, and that attacks this one, and that gets liberated. So you can generate the formation, you can monitor the formation of nitrofenolate, and this weight is there. Now that is one of the nickel kind of thing which we did in doing this. This is the concerted action of the double Lewis acid activation. Double means one this and one that, both at the same time. Getting that, we got excited after that 2009 paper. That looks like we have understood a little bit, maybe not 1% we have understood. Okay? If we have understood, now pay attention to a ligand. Between the two, the best ligand is the pyridyl and amine. Pyridyl and amine is giving the best. Pyridyl, pyrazole,